Hello, class. We are covering 2.1 functions in this video. It will be done in two parts, so take notes. Hit the closed captioning button if you need to. 2.1 functions. All right, so let's start off with the definition of a function. So here, a function, a function f is a rule that assigns to each element x in a set A. So x is in a set. We'll call it A. Exactly one element called f of x in a set B. Okay. So you're used to seeing functions written like this: f of x equals 3x plus 1. So what this is saying is that for every x that we plug into this function, we will get exactly one result. Okay, like if I plug in 2 for x, when I plug that into this function, then I get 7. I don't get 7 and some other number, right? I only get exactly one element. Okay. All right, so the set A. So remember, the set A is where all the x's are coming from. So the set A is the domain. Of the function. The range is made up of all f of x. So the results, you think of them as the y values, such that x is in the domain. Okay, so it's basically all of the results that come from all of the x values that are in the domain. So that if you plug in all of the x's in the domain, whatever the results are, those results create the range. So if it's not possible to get 0, then 0 would not be in the range. Okay. All right, so what we're going to do here is we're going to take a look at domain and range when we look at a graph, but mostly we're going to take a look at how to find the domain algebraically. Okay. All right, so here is an example of looking at a graph and determining what the domain and range are. Okay, suppose that I have this function, f of x is equal to x squared plus 4. Okay, so if I have this, then here, the domain, I don't have any restrictions. And we'll go over the restrictions in a minute. Okay, so the domain here is all real numbers. I don't have any restrictions. We don't have anything that says, oh, x can't be this, x can't be that. Okay, so there are no restrictions. So the domain is all real numbers. Another way to say all real numbers using this notation, you can just say negative infinity to positive infinity. The positive is not necessary in front of the infinity. That's just, back in the day, they used to require that. Not anymore. Okay, so the range here is all real numbers greater or equal to 4. Okay, so another way to write this is like this. Okay, greater than or equal to 4. Okay, and then here's a visual so that you can kind of see where all of this information comes from. It's a little easier to determine the domain and range by looking at its graph. Okay, so what happens is this function here is the parabola shifted up 4 units. So there's the vertex. There are 2 other points, and I get my parabola. This one looks kind of... Okay, and we get this parabola. Okay, so here we can see that the x values that are being used, this goes on forever, and this goes on forever, and it just keeps getting wider and wider and wider. Okay, and so here we can see all the x's are being used. If I pick an x value here, I'll get a point on the parabola. If I use an x value here, I'll get another point on the parabola. And as I go down to the left, I'll just go up higher and higher. Next value here, I get a point on the graph. Same thing here on the right side. If I pick a point here, I end up with a point on the parabola here, up there, and up higher, higher, higher. Okay, so we see that all the x's are being used to create this graph. When we look, so that's why the domain is all real numbers. When we look at the y values here, the range, we see that not all the y values are being used. We see that these values down here, these y values, are not being used. Okay, but we do see this one, 4, we see 5, 6, 7, 8. All of these y values go map somewhere onto that graph. Okay, and it goes up higher and higher. Point there, point there, point there. Okay, so here the range is 4 to infinity. Okay, because we see that these y values down here below 4 are not being used. Okay. All right, so let's take a look and see how we can find the domain algebraically. All right, so domain. Okay, so for the most part, it's going to be all real numbers unless you have restrictions. And we'll go over some basic restrictions. Okay, so all real numbers unless restrictions exist. Okay, so here are some possible restrictions. Okay, so all right, so one possible restriction, you might have x in the denominator. Why is that a restriction? Because we don't want 0 in the denominator, because if we get 0 in the denominator, then it is undefined. Okay, so x in the denominator is a possible restriction. Okay, we don't want 0. It's possible to have x in the denominator, and no matter what you plug into it, you won't get 0. Okay, so in which case then you're good. But you want to make sure. So you want to be able to check to see that there are no values that make the denominator 0. Okay, another restriction, if we have x inside the square root, so we don't want to take the square root of a negative number because then we end up with imaginary results. Okay, so we don't want negative. Okay, and then it is possible to have both of these together. You might have a square root in the denominator, in which case you don't want it to be negative and you don't want it to be 0. Okay, so just keep that in mind. All right, so let's take a look at some examples. All right, so let's find the domain of each. Okay, so we'll do 3 examples. Okay, so here, let's start off with this one. F of x equals 3 over x squared minus 4. Okay, so we have x in the denominator, and we said that that is one of our possible restrictions. Having x in the denominator, we don't want 0. Okay, so let's take a look. So here, we don't want 0. So let's figure out when this denominator is going to equal 0. Okay, so x squared minus 4, we don't want it to be 0. When does that happen? Well, I can factor this. X plus 2, x minus 2. Okay, and so we don't want x plus 2 to be 0. We don't want x minus 2 to be 0. So we don't want x to be negative 2, and we don't want x to be positive 2. Okay, so that's our domain. Our domain will be all real numbers except for negative 2 and 2. Okay, so our domain is going to be all real numbers except for negative 2 and 2. Let me show you what that looks like on a number line. So here's negative 2 and 2. So we said the domain will be all real numbers except negative 2 and 2. So that's what it looks like visually. So the way we write this, we're going to go ahead and use interval notation. And so we'll do one for this area, this first area. And then we'll do an interval notation for this middle area. And we'll do an interval notation for this third area. So the way we write that is negative infinity to negative 2, but we don't want to include the negative 2, so we use parentheses. Okay, and then we use the union symbol. And again, so negative 2 to positive 2, but again, we don't want to include the 2, so we will use parentheses. And then for this third shaded area, 2, not included, so don't use the bracket, use the parentheses, all the way to positive infinity. Okay, so this would be the way to write your answer. Okay. All right, so let's take a look at this next one. Suppose that you have this function, f of x equals square root 3x minus 5. Okay, so we do have one of our possible restrictions. We said up here, we don't want x inside square root to create a negative. So we have x under the square root, and here we don't want this to be negative, because if we have square root of a negative number, then it is imaginary. Okay. All right, so 3x minus 5, we want it to be 0 or higher, right? So greater than or equal to 0. We don't want it to be less than 0 because less than 0 is negative. Okay. All right, so let's go ahead and solve this. Let's go ahead and add 5. 3x is greater than or equal to 5. Divide both sides by 3. X is greater than or equal to 5 over 3. Okay, so that's our domain. Okay. If you graph this on a number line, here's 5 over 3. So x can equal 5 over 3, so this will be a closed circle. And all of that, right? So the way we write this in interval notation is we say 5 over 3 up, bracket, because it's okay for x to be 5 over 3. So we will use the bracket this time instead of the parenthesis, and then positive infinity. So this is how you would write your answer. Okay? So again, it can equal 5 over 3 because when x is 5 over 3, we get 0. When you plug in 5 over 3, the 3's cancel out. You're left with 5 minus 5, which is 0. Okay? Square root of 0 exists. Square root of 0 is 0. Okay, so it's okay to have 0 in the square root. The thing is, we don't want it to be negative. Okay, so if you choose a number over here, down here, like 0, if you plug in 0, you end up with negative 5. Square root of negative 5 is imaginary, so we can't have 0 as part of our domain. Okay? All right, and let's see an example where we have both of those conditions to think about. So f of x equals 2 over a square root of x plus 1. Okay, so we don't want this to be negative. And we don't want it to be 0. Okay, so we don't want negative because it's under a square root. But also, we don't want 0 because it's in the denominator, right? So there's two things here. We don't want it to be negative and we don't want it to be 0. So what we do want is we want this result, we want it to be greater than 0. We can't say greater than equal because we just stated here we don't want it to be 0. So we can't have that. We don't want it to be negative, which means we need it to be greater than 0. Okay, and then we can solve this. So x is greater than negative 1. So our domain, here's negative 1, open circle, and all the values that are greater than negative 1. So in interval notation, we have to use the parentheses, not the bracket. And we go from negative 1 to positive infinity. Okay? So just be careful here. We don't want it to be 0 because it is in the denominator, and we also don't want it to be negative. Okay, so make sure you see the difference between that one, letter C, and this one over here. When we don't want it to be negative, we do use the greater than equal. It's okay for it to equal 0. Okay, it's a closed circle. But here, we don't want it to be 0. So it has to be strictly greater, not greater than equal. And it will be open circle, not closed. Okay? All right, let's take a look at evaluating functions. All right, so let's take a look at this example over here. Let f of x equal 3x squared plus x minus 5. So here's our function. And let's go ahead and find the following. All right, so letter A. Let's go ahead and find f of negative 2. Okay, so here, when you see something like this is not a multiplication. This means that x is negative 2. Okay, so you're replacing this x with negative 2. So that means you have to replace these x's with negative 2. Okay? So instead of writing 3x squared, I'm going to write 3 times negative 2 squared. So 3 times negative 2 squared, and then plus negative 2 minus 5. So all I did was replace all of the x's with negative 2. And then we work this out. Remember, order of operations, you have to do exponents first, then you can multiply by the 3. So 3 times negative 2 squared is 4. 3 times 4 is 12. 12 minus 2 is 10. And we get 5. Okay. All right, let's try this one. Let's find f of 0. F of 0. So that means I have to replace all of the x's with 0. So I'm going to do 3 times 0 squared plus 0 minus 5. So 3 times 0 plus 0 minus 5. So that's 0 plus 0 minus 5. And that's just going to be negative 5. Okay? All right. Go ahead and try this one. F of 4. So hit the pause button. Let me bring this down so you can see the function. Hit the pause button and go ahead and work this out. Come back and see if you have the right answer. Okay, so 3 times 4 squared plus 4 minus 5. So exponents first. So that's 16. 3 times 16 is 48. 48 plus 4, 52. 52 minus 5 is 47. So you should have gotten 47. Okay? If not, go back and check your work, see if you can find your mistake. You should be able to. Okay. Go ahead and try this one. F of 1/2. Fractions. Fractions are fun. Fractions are our friends. Okay, go ahead and hit the pause button and give this a try, and then come back and check your answer. All right, so this is 3 times 1/2 squared plus 1/2 minus 5. Exponents first, so 3 times 1/4 plus 1/2 minus 5. Multiply 3 times 1/4, so this is like 3 over 1. So multiplying across 3 times 1 and 1 times 4, I get 3 over 4. I'm going to write this 5 as 5 over 1. Okay? All right, now my LCD between 4, 2, and 1, the LCD is 4. So I need to turn all of those into fractions, equivalent fractions with a denominator 4. This one is good. This one will have to be 2 over 4, which is equivalent to 1/2. And then this one will be 20 over 4, which is equivalent to 5. Okay. And then when I add and subtract here, I get 5 over 4 minus 20 over 4. And my final answer is negative 15 over 4. Okay, so you should have gotten negative 15 over 4. Okay, so that is it for part 1. Part 2, we're going to talk about piecewise functions and net change. Okay, I will see you in a bit.